Hello and welcome to quite a tricky one. This is searching and sorting algorithms. So this is something that always causes people huge amounts of aggravation, but you being a talented bunch will cope with this really well. So I'll jump straight in and let's just have a look at this guy here. I'll throw that on there. Please introduce yourself in the comments. Hi Hayden. Yeah, get yourself sorted out. That's absolutely fine. This is just a warm-up act, really. It's going to be a short warm-up act because there's quite a lot to get through. And I suppose the aim today is that you understand what these different searching and sorting algorithms do, how they operate, advantages, pros and cons. And I've got some pseudocode as well. I'm probably not going to have time to whiz through the pseudocode, but you will have this PDF. Hi, Decent, how are you? Thank you for coming. I'll send you the PDF through so you can have a play with it and see, just to make sure that you understand it. And I just said the pseudocode in there, if you're aiming for a 7, 8, 9, trying to get your head around the pseudocode is probably what it's all about. Yeah, I slightly changed the syntax of it. I slightly changed what we're doing today because you know I missed Paul Burner, handsome as ever, missed you. Change slightly what I'm doing here. So what's this? Look at this. What type of, sorry, that's the answer to the question. Well, it's Decent. Shall we see if you are correct? Is it a syntax error? Decent, you are a superstar. I thought you were talking about searching and sorting syntax. So yeah, the answer is syntax. So I'll shut up and go to the next one. How about this one? I think this is the one before we jump into it. In a flowchart, what shape would you use around does the password contain a number? Is it A, a diamond, B, a rectangle, or C, a square? What do we think? Do please say hello in the comments if you are here. We have many lurkers as per usual. What do we think about this? Decent is on fire. He's literally on fire. He says it's a diamond. Do we agree with this? Let's wait and see. You are again absolutely outstanding. All right. So we've got some quizzing at the end, but today I'm going to jump through this. This is from the specification, and we are going to do binary and linear searching and bubble merge and insertion sorts. Yes, you were spot on, Hayden, and so were you, Ishak. Hi, Ishak. You can have your applause too. There we go. All good. Oh, I can make that full screen. Let's have a look. There we go. That's a bit more real estate, isn't it? Is there a typo? Anyway, so these are the two areas I'm going to look at today. There wasn't a question on this in the mocks, so I've got in last year's exam. So I've got a sneaky suspicion it might be in this one. So let's jump in and have a look. We've got two sorts of searching algorithms, and without stating the obvious, but I think it's probably worth mentioning. A searching algorithm is used to search through data to find a particular item. And we've got two ways of doing it. And of course at GCSE, you're only looking at two, and these are fairly straightforward. So we're going to look at linear search and binary search. And what they might ask you to do is describe how a linear search works or show how a linear search works and talk through the stages. So in the simplest possible terms, right, when you think about a linear search, it works in quite a simple way. First of all, it identifies the length of a list, how many items are in it, and then it starts, guess what, at the first item, and it looks at the value. And these are literally the steps. It then compares the value of the first item. Dog's broken in. Compare the value of the first item with the search item. So if the first item is 5 and it's looking for 15, that's not the search item. But if it is the search item, the search ends. And if it's not the search item, it increments, which is the fancy word for increasing the counter. So think about for I equals 1 to 10, it increases the counter from 1 to 2 to 3 to 4 to 5. Literally, it counts upwards in increments. And it repeats steps 2 to 5 until it finds it. So there are steps 2 to 5, these ones here, and it repeats these steps until it finds the item. And it continues until the end of the list. Ishak, you are a man of great wisdom. That is exactly what it is. So from what you've said there, you get it. It goes one by one. But make sure you can describe it in terms of these points, because when they mark this, if they say describe it, they will look for you to say, first of all, that it identifies the length of the list. Then it starts at the first item. Then it examines that value and so on. So these literally are the steps that you've got there. So that's what you'll need to use if you're going to describe it, okay? So that's the kind of simple way of looking at a linear search. Whoa, steady on there. Let's go back. So here we can see an example worked, okay? So the logic here is that you start from, well, I had asked him to stop, but he seems to have got the message now. Probably wants his tea. So the point here is you start from the leftmost element. Here is the leftmost element, which is number 10. And notice this is the index. This is the, when you talk about the counter, it increases by 1. So this is item 0 in the list, which is called an array. This is a 1D array because it's one line of data, okay? So it's searching this array. And let's say, for example, in the example, it says it is searching for the number 5. So it's going to go through them one by one. It'll find out how many items there are on the list, and you've got 8. You've got an index of 8. So it will start at index 0 and it'll work its way through. Is what's at index 0, in other words, number 10, is that the same as 5? No. Go to the next one. Is it the same as 6? No. And so on. Is it the same as 5? Yes. End search, okay? So that's how the linear search works. All you got to do is make sure that you can explain it in those simple terms. That's it. Okay. Linear search, I'm not going to hang around on because it's the easy one. And I put last week's live stream onto YouTube. It's there for you, and I sent you the PDF. I'll do the same today, okay? This, incidentally, is the pseudocode for the linear search. I don't intend going through this now, but if you are aiming for a 7, an 8, or a 9, spend 5 minutes working through that. Bear, dear man, how are you? Very good to see you. If we're lucky, we can get decent to do a... Do you have to remember what, dear boy? No, you don't have to remember the pseudocode, no. But you do need to know, it would be helpful if you can recognize it. So I think the place to get to, so they're not going to ask you to write a linear search in pseudocode. They'd never ask for anything that complex. But they might put this in there and expect you to recognize it as being a linear search at the higher end there. Like I said, grade 7, 8, 9. So it's just useful to look at that. So in your case, Decent, spend a minute or two going through it and thinking, okay, I could recognize that as a linear search, but you're not going to have to create that in pseudocode. All right. Last thing for linear search, and this is the last thing they can ask you, and they like to ask this because it's easier to mark, is green advantages, red disadvantages. So if you can go in with an idea of a good and a bad thing about each of these searches and sorts. The linear search is simple. It works on sorted and unsorted data items. So for example, 6, 12, 19, 23, 84, they are sorted. 1, 5, 2, not sorted, unsorted. So you've got two sorts of data that you can be searching, sorted or unsorted. So this one works on sorted and unsorted data, and it's suitable for small data sets. The problem is it's a slow algorithm, and the larger the data set, the slower the algorithm, literally, because it's going one by one by one. So if you're searching 10,000 items and it's the 9,000th and it's the 10,000th item, you'll be searching for a long time, okay? So that's the disadvantage there. So make sure you've got a sense of what the pros and cons are of each one. Number 2 is binary search. So this is where you go to the middle and you discard either the left or the right. So I'll whiz through the principle and then I'll show you an example, okay? So the first thing you've got to do is you take your list and you halve it to find the midpoint, and you round up if it's an odd number in the list, okay? If the search value is the middle item, then the search ends. That's fairly obvious, isn't it? However, you then do this. If the midpoint value is less than the search value, the lower half of the list ignored, and the search focuses on the top half. And if the midpoint value is greater than the search value, the top half of the list is ignored, and the search focuses on the lower half. So it takes the midpoint and it asks the question: is this the number? No. Okay. If it's not the number, is the number bigger or smaller than this number? And depending upon the answer, you're then going to chuck away the other half of the list. So in one fell swoop, you're ditching half the data. So you can see how this is going to be faster than the linear search that we looked at, but it's a bit more complicated, okay? And of course, so this description you are going to need. And this part here, they love you to get you to describe this in the exam, okay? And then after that, the process repeats until the search item is found or the search item isn't in the list. Because of course, the item you're searching for might not be in the list. You often search for a document and actually it's not there, it's somewhere else. So the search item might not be in the list. So I hope that makes sense. That's the principle of your binary search. Find the middle point. Is that the item you're looking for? No. Is it great? Is the thing you're looking for bigger or smaller than that middle item? If it's bigger, get rid of everything that's smaller. If it's smaller, get rid of the half that's bigger. And then keep doing the same thing. So then you go to the middle point again. Is this the item? No. And if the middle point, if you can't easily find the middle point, you simply you go up one, you round up, okay, if it's an odd number of values. Any issues, shout at me, but that's the binary search for you. So it's more efficient than the linear search, but here's the negative thing, is that the list must be sorted. So this list has to be sorted in order. You can't do this on an unsorted list, which is a problem with it. You might want to sort the list first. So there we go. Here it is in words. Find the middle point, compare the middle to what you're doing. If it's bigger, ignore the right part, otherwise ignore the left part, and repeat the process until you found it. That's a bit repetitive, actually. So here we go. Let's have a look at this guy up here. Same principles here. This time we've got the index down here. So this is the point. So this is number 0, number 1, number 2, number 3, number 4, and then you happen to have the numbers up here, okay? So you find the middle point, which is here, and then you ask, what are we looking for? We're looking for number 3. So number 3 is here, right? That's the index, excuse me. The number 3 is here. So you go to the middle point, which is 5, and you ask the question, is that the number? No, it's not, because we're looking for 3. Is 3 bigger or smaller than 5? Well, it's smaller than 5, so therefore we can get rid of everything that's bigger than 5, which is all of this stuff here. All right? And then we do the same thing. What's the middle point? Well, there isn't a middle point, so we'll go up and we'll look at 3. Is 3 our number? Yes, it is. Search ends. Got it? Work through it a few times so it makes sense to you, but that is the principle of the binary search. And there we go. It found it there, found the number 3. Got it? Again, if you are a 7, an 8 or a 9 person, have a look at the binary search in pseudocode. You don't need to learn this off by heart, but look at the giveaway here. What does the div stand for? Divides it by 2. So and look at the greater than and less than over here. We've got less than actually. Yeah, so that's just to recognize that it's the binary search. I don't want to go through that now because we run out of time really quickly if I go through line by line by line of pseudocode. That's a good little job for you to look at if you want to get a 7, 8 or 9. So just to recap, more efficient than a linear search, and you can see why it's more efficient because you haven't got to go through every single item. You're halving it each time, but it only works on ordered lists. And for smaller data sets, it's not that efficient because it's doing quite a lot of work. So if you're only searching 10 items, it's quite a lot of faff. But when you've got huge data sets, this is a more efficient way to search. We are doing well. We're into sorting now. Where are we? 44. Bonus. All right, sorting. we're going to look at three sorts. We've got bubble, insertion, and merge sort. And again, they will ask you to either describe it or to actually complete one, and they could ask you about advantages, disadvantages. That's what they tend to focus on in the exam. Right, bubble. So let's do the sort of broad spectrum bubble analysis. A bubble, and the idea of the reason it's called a bubble is because it bubbles gradually towards the surface. Okay, so here we go. So this is to sort data now. We're not searching for data. This is to sort data in order. Okay, so you've got an unorganized list, and you want to put the items into order. So say, for example, alphabetically or numerically, all right? So you know when you look at your file menu, and if you're sensible, you've ordered your file names by year, month, day, year, month, date. Then when you click on sort, it'll sort them numerically in that way. So that's what we're looking at here, okay? No. Right, no, that is a good question. And that's why I made the point of, I'm pleased you've asked that, Ishak. So the first ones that we did were the searching algorithm. So that's when you're searching for an item in a list. Now what we're doing is we're sorting items in a list. We're putting things into a particular order, okay? That's the difference. So these are algorithms that do two very different things. Things that you would do on your computer. You might search for a file name, but you might also sort your items into order by date, for example, or by size. You know, when you're trying to get rid of stuff off your PlayStation or your Xbox, and so you organize it via biggest game first, and you think, well, I don't play that. That's 68 gigabytes, so I'll delete that one off. So that's what we're looking at. It's a good question, though. So these are things that you actually use every time that you go to a computer. So now we're looking at sorting, all right? And we're going to look at three sorts. The first one's the bubble. So this is the way it works, to sort things into an order, A, B, C, D, E, or 1, 2, 3, 4, 5, or 10, 9, 8. Indeed. Let's have a look at it, right? So you start at the beginning of a data set, and I'll show you an example, right? I've given my two classes the that PDF, you know, that lovely colourful PDF. So have a look at that. And if you want a copy, just let me know. So you start at the beginning of the data set, at the beginning of your list, and you compare the first value with the next. And as you said, Hayden, this is looking familiar, isn't it? If the first value is bigger than the next value, you swap the position of the values. And you move to the second value, and you repeat step 2 to 3. And you go through the entire set doing that. But the problem is, you do it the first time, and it still won't be sorted. It will have improved it will have slightly improved the way that it's sorted, but it won't have sorted the entire data set because it can't do it necessarily in one pass. So it'll go through the data again, and it'll look at the first value and it compare it to the second value. And if the first value is greater than the second value, it'll then move it beyond it. And then it'll keep comparing and go through. And so it might make multiple passes through the data. And then once it makes an entire pass of the data without making any changes, that's when it knows that the bubble is completed, okay? So that's how it works. Again, take some time to look through these steps. And you know, all of these searches and sorts that we look at, it's got a routine, and it completes the routine until it finds it. And in this case, it does this, and then it will make repeated steps, repeated passes. I can't actually get over there. It'll make repeated passes until it's actually cleared the data. And the way the computer knows, and the word knows is nonsense, but it's completed when an entire pass is made and nothing's changed. That means there's nothing further to change. Does that make sense? That is your bubble sort. Like I say, I predict there's going to be a question in this. So here it is. Simple algorithm. The first loop would produce 3, 2, 4, 1, 5. So what we're looking to do is to put these in the right order. So let's have a look. Cast our minds over here. So it's going to look at item 3, and of course we want to have this being 1, 2, 3, 4, 5. Agreed? That's when the thing starts to be that's when it would be sorted, when it's 1, 2, 3, 4, 5. But currently it's 3, 2, 4, 1, 5. So what does it do? It looks at 3, which is here, the first item, and it compares it with the second item. And it says, is 3 bigger than 2? Yes, it is. So I'm going to swap it. What does it do then? It compares the next two. It compares the 3 with the 4. Does it need to swap? No, it doesn't. It compares the 4 with the 1. Is 4 bigger than 1? Yes. Ishak, your questions are excellent. And that is exactly it. So it will need to go through that. So you can see on the first pass, on the first pass of this sort, the data will be more sorted, but it won't be entirely sorted. So it will do as many passes of the data until it's completed. And the computer only knows it's completed if it does an entire pass and makes no changes. Therefore, the data is sorted. All right? Does that make sense? Again, spend a bit of time looking through this slide, but it's literally going through it. And let's have a look. Hayden's point here, this is really a relative of the linear search in that it's going through it in step by step by step by step by step. And you know, when you're thinking about advantages, disadvantages, you can already think, well, this is going to take quite some time to do, isn't it? Because it's got to do multiple passes and it's got to do a whole pass without changing anything. Yeah, that's quite painful. And if you've got a massive data set, that's a lot of work, isn't it? But it's quite simple to code, isn't it? It's quite a simple algorithm. So that is how it works. How am I doing time-wise? We're doing okay. All right, so that's your bubble sort. And there's more here. This shows the entire thing being done. So now we're looking at the second loop of the algorithm. So we were left with, after the first loop, 2, 3, 1, 4, 5. So we can see 2, 3, well, that'll stay the same. It compares 3 to 1. Decent says, wait, so it doesn't have to go through only twice. It can do more. Yes, exactly. It will go through as many times as required, right? And here's the key thing, which we're getting to now, is that the only way the algorithm knows that the search has been completed is when it doesn't have to make any further changes. So when we look at the pseudocode, again, if you're after a 7 or 8 or a 9, look at the flag in the pseudocode that says, that sets it to complete. There'll be a flag which will only get raised once it goes through the entire data set and makes no changes. Got it? So that's your challenge, you 8s and 9ers. Does that make sense? So it may be it's only got to go through once. It may be it goes through once, makes no changes, and it's sorted. Otherwise, it'll go through as many times as needed and then through the extra time to make sure that it makes no further changes. So if you look at it bubbling, see why it's bubbling? Because it gradually sort of, well, it doesn't bubble to the top because it's going from side to side, but you can see how it's it's like a Mexican wave, one of those very annoying things at football matches. So 3, 1 will become 1, 3. 3, 4 will stay the same. 4, 5 will stay the same. So the second pass, we end up with 2, 1, 3, 4, 5. It's worth spending some time on this. Then we go, so 2, 1, 3, 4, 5. And this is probably going to be our last pass now, our penultimate pass. And then for the last time, it says, is 2 bigger than 1? It is, so it swaps it. That's okay, that's okay, that's okay, and that's okay. And that will go through. And then the algorithm runs again, and there'll be no swaps. So your final list will be 1, 2, 3, 4, 5. But you knew that because you're smart, okay? So this is the pseudocode. And those of you who are super smart and are ahead of the game here, see this here? This sorted equals true. And look at this bit of code here. See, sorted equals false. While sorted equals false, da 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 da. And then this is the bit of code. So have a look at that. That's that flag that says, right, I've checked it and we've had to make no changes. So so it's done. So look how they've used a for loop here. For sort count equals sort list to length minus 2, blah, 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 blah. So have a look at that. And whoa, where am I going? Have a look at that, and that will be what you need to do. Blimey, I stepped back miles there. Bubble, 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 bubble. Okay. So again, pros and cons. Don't worry too much if you don't recognize it in pseudocode. That is at the very top end. Okay. But again, this you do need. Easy marks in the exams. It's a simple sorting algorithm, 1 mark. It's easy to code, 2 marks. But it's memory intensive and it's slow for larger data sets. If you're searching thousands and thousands of thousands, does that make sense? Good. If you're searching huge data sets, it's going to take blinking ages. Right, insertion sort, it's our last one, isn't it, I think? Yes, it is. Insertion sort, we've got through this quite quickly, actually. So this, again, you'll recognise part of this from some of the other ones that we've done. So this one I'm calling the compare in turn algorithm. So this is called the insertion sort. So in this one, you've got an unsorted list. So 1, 6, 4, 9, 3, 2, 4, right? Compare the second value in the list with the first value. If the second value is smaller than the first value, the second value is moved left until a value on its left is smaller. Now that sounds a bit complicated. We have merge as well. Oh yeah, we've got merge as well, haven't we? Okay. And the sort process repeats with the next value. So let's have a look at an example which might be a bit easier. Incidentally, if you Google these searches and sorts online and type in animation, watching it just going through its process, you might find you suddenly go, oh, okay, I see. And that's helpful because reading the words isn't always good. Doing it with a deck of cards or with a bunch of numbers can be quite helpful. So the insertion sort, it's similar to the bubble sort we just looked at, but where the bubble sort finds the next largest or smallest element, an insertion sort takes the element and places it into a sorted list at the beginning of the array. So the first element in the array or the list is always considered sorted as it is the only element. And then we move on to the second one, which we compare to the first. If the second is smaller than the first, we swap the 2 elements. Otherwise, we leave them alone. All right. So you might find it helpful to look at an animation of that happening. So assume 85 is a sorted list of first item. So look at what happens there. It then looks at 12 and it decides to place it in front of it, okay? It then looks at 59 and it places it between it. It then looks at 45 and it places it between the 59 and the 85. So it's literally working down the list and inserting. Ishak, I could hear myself explaining it and I wouldn't get it if I listened to myself. I'd recommend looking at the first couple are conceptually quite easy to understand. This one is a lot easier if you just look at the diagram. Look at what's happening, okay? Let's go back up to here. But I'm glad that you are telling me when it's not making sense, because that means I can go back and look at it again, right? So look, this is an unsorted list. So it looks at the second item and it compares it to the first, and it asks the question, is the 12 bigger or smaller than 85? And the answer is, it is smaller than 85, so it gets put in front of 85. Then it goes to the next item, which is the 59, and then it compares it and it says, well, where does that need to go? Well, it's between 12 and 85, and then it's working its way all the way down, okay? So if you work your way through that and have a look at it after let's have a look at this. So the numbers coloured blue means the program, yes, exactly. Look at an animation for it, that will help as well. The insertion sort, it is the idea that it's just going through it and inserting it into the right place, okay? So that is your insertion sort. And I think what this has identified probably is that that's the one that you need to go and do a bit of extra work on. So this is the pseudocode. We're at 59, so I want to try and get through this. Again, if you're after your 7, 8, 9, have a look at this and see if you could put them side by side. Okay, not in practical, which means that when you next come into a lesson and I give you like a 10-minute or 15-minute revision bit, grab the blue CGP book and then grab the white CGP book from my room and work through a couple of examples, all right? And I'll do some past papers and give you some past paper practice on this as well. But that's good. We've identified that you're sorted out apart from that one. So that's useful in itself. Practice. And would you be able to show how it's done in the if they gave you an example? So on this one, it's more efficient than Bubble, it's less complex than a merge sort, and it's less memory intensive. Suits small data sets, but it's less efficient than a merge sort. Yeah, have a look at it. Have a look at it in your revision. I honestly think that with some of these, looking at an animation of it happening can just really help. Okay. Yeah, paper one. Did I say paper two? Paper one. All right, good. Okay, so last one, I think. I've lost count. No, sorry, this is the merge sort. We're still talking about it. No, merge sort, divide and conquer. Okay, so list split in half until all elements separated. Right, I'm confusing myself now. This is the last one, merge sort. We've just done insertion, haven't we? This is merge. So merge is, in simple terms, all of the elements are separated into single units. So if you've got a list of 8 things, you break them down into 8 separate units. You then compare the individual elements as pairs. So you split them all up, and then first of all, you compare the pairs. So you put the pairs in order. Then you take 2 pairs and you turn them into a 4, and you put that in order. You then bring together the 2 4s, and so on. And that's actually how it works. So let me run through it and see, give me a shout if this makes sense. First step is all of the elements are separated out, okay? You then reform. The first step is you take the individual elements and you pair them. So if you've got a 5 and a 4, you would pair them and then turn them into 4 5. Okay, so you're then going to end up with a whole set of sorted pairs. That's the next bit. So the pairs are sorted into order. Okay, they are compared, and then they're put together into 4s, and then they are sorted, and then the 4s are put together into 8s. So it breaks it all the way down to individual elements, and then it pairs them, sorts them, brings them into 4s, sorts them, brings them to 8s, sorts them, brings them to 16s, sorts them. And that is how this one works. I'm hoping that makes sense to you. So can you see, I reckon this is probably, sometimes the images help a great deal. So can you see, we've got the unsorted list over here. And you can see it's unsorted because it's 2, 45, 6, 9, 15, 12, 7, 8, right? So the first thing it does is it, this diagram, is it helpful? No, actually, it's split individual lists. Yeah, 245, 245, 69, 245, 69, divided 69, divided 69. Actually, no, that is not a particularly good, that's not a particularly good example there, I've just realised. Yeah, okay, never mind for that one. So this one, the merge, let me see if I can find a, I'll find an animation for you which works a lot better. So the merge sort is most efficient for large data sets. It's got a consistent running time. So regardless of the size of the data set, it's got a pretty consistent running time. But it is a complex algorithm. It's hard to code, or it's more difficult to code. And it's, if you've got a smaller data set, it's slower. Can you see how these advantages and disadvantages are almost the same, but for, you've got the same list. This is all paper 2 algorithms. Yeah, this is paper 2. this is, let's just go back up to here. It doesn't require you to, right, yeah, sorry, this is 2.1.3. I said 1, didn't I? This is paper 2. So this is 2.1.3. So this is searching and sorting algorithms, okay? This isn't paper 2, it's paper 1. Because this is to do with, because it's algorithms, and paper 2 is to do with algorithms, that's why, okay? Which is why, if you struggle a bit with the coding, this is a really, really good way to get extra marks. I want to go back to this just to see what they've done here. 24569, 151278. No, okay, no, right, I'm being an idiot. All right, so, right, let me, yeah, and you know what is in paper 1 is also the system security stuff as well. Right, okay, I've got my head around this. I didn't quite recognise what was going on first of all. So look, this bit here, this first part from here to here is simply splitting the list into individual elements. I've never seen it taken quite such a long way before. But what it's saying is it's taking the entire list, it splits it into ever smaller numbers. So it goes from 8 to 4 to 2, and then these are the ones here, okay? It then sorts them in pairs. So can you see 245 remains unchanged, 69 remains unchanged, but here, this one goes from being 1512 when they're individual elements to 1215. So they're compared as pairs. And then 78 remains the same. You would have thought they could find one where more things get changed. So what it then does is it brings these two elements here together as 4. So 24569 becomes, ooh, I can use my arrows, hang on a second. This becomes, so we're going to focus on this bit here. Are you all still with me, or am I just waffling? This, come on. So we're looking here, and this 2 goes down to here. The next one is the 6, which goes to here. The 9 goes into here, and the 45 goes into there. And it does exactly the same thing on this side here. And then it finally merges these two together to produce this. Does that make some kind of sense, ladies and gentlemen? So just to recap, the first step is it splits it into individual elements, which is what we end up with here. So this list here is the same as the one at the top. And then it first of all sorts them in pairs. It then sorts the 2 pairs into a 4 and the 2 4s into an 8. Okay, that's it. That's the merge sort. I think I made it more complex than it needed to be. And those were the advantages and disadvantages. I hope that makes some kind of sense. Let's have a look at something more fun, shall we? So what about this? Come on, computer. This shows a nearly completed merge sort. What 4 values will appear in the yellow box? What 4 values will appear in the yellow box? This will demonstrate whether you have made any sense of what I was going on about. What have we got? Ooh, Deason's got an answer. He's got 2, 4, 5, 6. Do we think that Deason is correct? What do we think about that? Do we think Deason is accurate with this, or is that a complete lie? We've got Ishak saying, oh, hang on, we've got 2546. We've got Ishak saying 2546. Should we see if they are correct or incorrect? The answer is 2456, 2456. Absolutely spot on. That is outstanding. What about this one? Look at the diagram below. How many iterations would it take a binary search algorithm to find the value 19? Now, they could ask a question like this. What do we think? Binary search algorithm. How many iterations would it take? How many iterations of the algorithm do we think it might take? So we've got Ishak who reckons it is 3. Any more takers? We've got Decent who says 3. Are we fairly convinced by 3? Shall we have a look? The answer is 3. That is outstanding. Okay, what's that? Look at this one. What type of search algorithm can be carried out on this data in its current form? What is it testing with this question? What's it testing here? They do like to, they definitely like to test your knowledge of this part. Okay. And I guess Decent said binary, Ishak has said linear. Both binary and linear. Hayden linear. Can anyone tell me why they think it would be linear? And that's not me making the whining noise, just to be clear. Not binary, just sorted. Okay. We've got Decent saying no, just linear. So the answer is a linear search, okay? Not binary, not sorted. Exactly. Binary needs a sorted list, okay? Linear doesn't. Linear just goes through in order. All right, good. Important to try and get that one right, okay? What have we got here? Question 4. A company has thousands of customer entries in its computer system. Each customer has a 10-digit ID number, which the company uses to sort the list of customers. When a new customer signs up, their details are added to the end of the sorted list. Which algorithm would be best to use to make sure the list remains sorted? Could I have a which algorithm and bonus for a why? Which algorithm and why would be handy? Which algorithm and why? So, Ishak has gone for merge. What a good man he is. Ishak's gone for merge. And then we've got Hayden's gone for insertion sort, because the number could be anywhere in the list and will only be appending numbers. Okay. Merge sort, some very good answers here. Merge sort as it's the most efficient in long lists. So guys, we're all thinking along the right lines in terms of the way to approach this, but the answer is insertion sort, which means that Ishak and Decent, your homework is to go away and look at those definitions again and figure out why an insertion sort would be the appropriate one, okay? It is challenging, this, but the nice thing is if you can get your head around this, these are sometimes 5 or 6 mark questions. So they sometimes cover half a grade boundary. Well, 8 marks for a grade boundary or 7, so it can be 2/3 of it. If a computer, about 5 minutes. Okay, cool. If a computer has my tea is ready. If a computer has a low amount of memory, but you need to sort a large number of items, so they could do this sort of thing, you probably avoid which algorithm? This is quite a nasty one. Any idea? If a computer has a low amount of memory, a small amount of memory, Decent has gone straight for merge. A small amount of memory, but you need to sort a large number of items, you probably avoid which algorithm? And we've got Ishak going for merge. Any more takers on that? Any more takers on that? Nope. Okay, so let's reveal. The answer is merge. So that's outstanding. You guys are on it. That is good. That is good. That's good. That's good. Right, we're almost there. I think I've got one more question. I've got two more questions. The diagram shows the passes of an incomplete sort. By the way, if you're getting these right, you kind of get this. The diagram shows the passes of an incomplete sort. What type of algorithm is being used? What do we think, ladies and gents? Hayden has said, oh gosh, decent said bubble. Hayden said bubble. Let's see what you've got. You are correct. And Ishak said bubble too. So this means that you are absolutely on the right tracks. Right, that is it, guys. You have completed, what did we do? 45 minutes. Yes, indeed. Changes are consecutive. That is absolutely spot on. I applaud you all for giving up 45 minutes of your Tuesday for this. I think we've identified the insertion was the one that was slightly wobbly, possibly because of my explanation, but that's the one you need to go back and look at, okay? So, well done. I will send you the PDF. I'll put this on YouTube in the next hour or two. Make sure that you know the advantages and disadvantages. Guys, it's been an absolute pleasure, and I will see you again same time next week. I changed it to doing the bubble sorts and the searches, the bubbles. I ended up doing this because I thought this was more challenging and you guys could probably do with it. And I think that's kind of probably the case. So have a lovely evening. I'll see you all tomorrow. Cheerio, guys. Be good. Bye, 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 bye.